welcome back. Let us start with the session of the afternoon. And it's a pleasure to introduce Ethan Cotterill from UNICAMP, Campinas, with the talk Matroids, semirings, and curved singularities.
So thank you very much for giving me the opportunity to speak at this conference. I was involved in organizing a conference 10 years ago that was mentioned yesterday. And it's nice to see that some of the people who were at that conference previously are back in Rio again. So to start with, I want to contextualize what I'm going to be talking about. Hopefully by the end of the talk, the words in the title will sort of all fit together. In general, so we're always going to work over the complex numbers. In general, if I have a projective algebraic variety over C, it's often interesting to look at the space of morphisms, let's say of a given degree, from P1, the Riemann sphere, to X. And specifically, we might ask questions, for example, about its topology. Well, if X is Pn, then maybe this space isn't so interesting because every map from P1 to Pn, let's say every non-linearly degenerate morphism of degree d is just given by a vector space of degree d homogeneous polynomials over P1. So the upshot of that is that you can think of the space of morphisms of given degree as either an open subset of a Grassmannian or maybe a frame bundle over a Grassmannian. But things start to become a little more interesting if we start adding more conditions. So by way of notation, I'm going to refer to this space as M and D. This reflects maybe the notation that you'd expect from Brill-Noether theory. Well, this Grassmannian is homogeneous, so its topology isn't very interesting. But something that's a little bit more interesting happens if inside of M and D, we restrict ourselves to maps whose images have arithmetic genus G. So this is what I'm going to refer to as a Severi variety. And this terminology reflects what happens when the ambient dimension is 2. So if n is 2, this object is classical. And sort of the basic topological question we can ask, the most basic question is just whether this space or this variety of morphisms is irreducible or not. The point being that, for example, so some answers. First of all, if the ambient dimension is 2, it always is irreducible. And that is a very famous result of Joe Harris from the 80s, essentially. And moreover, what happens in the case of the planar severity variety is that you can say something more precise. So M2 dg is the closure of the space of maps with g-nodal images. So I'll just call this g-nodal maps. Where by a node, I just mean a simple double point. So think this type of behavior. Okay. But then one of the main points of what I'm going to talk about today is that as soon as the ambient dimension is at least 3, then in general, this is definitely not an irreducible variety. And I want to explain and sort of refine that answer today. Okay? And in order to answer no, the basic tool is going to be dimension counting for subloci of this space, MNDG. So we're going to refine our space of maps even further. And actually, so we're going to consider the following objects. This space is going to mean sort of maps that have a unique singularity in the image, for which the singularity has value semigroup or semiring, depending on your preference, equal to this S. And I'll explain what that means precisely. Okay, so the first thing I'd like to do is explain what value semigroups and semirings of singularities are. And in fact, yeah, so I guess in a way I'd be happy to just talk about what I'm going to call semirings, but semigroup is sort of the classical object, so say a word about those. And also how these relate to how you recover the genus of a singularity, or in other words, the contribution to the arithmetic genus from this combinatorial object. So to start with, let's just think of the case of unibranch singularities. So by branch, I mean, yeah.
What's the meaning of general? I think what?
I just mean it's not necessarily going to be irreducible. I'll give concrete examples. Well, yeah, where it's not. Okay. Okay, so if there's one local branch of our singularity, so I mean a cusp, something that looks like this, or maybe if you are more comfortable with Riemann surfaces, a surface with a corner. The normalization is always going to be P1, so this really is sort of the local picture. So if we consider a map near a singularity of this type, let's say the preimage is P, well, I can specify this map locally by power series in a local coordinate around this point P. So So locally, the singularity is parametrized by, let's say, some map psi of power series. And of course, this is just the same thing as dually as a map of rings. So if I map polynomials in the variables, affine variables of my ambient space, I just send xi to psi I. And the point is that the image of this ring map, whatever it is the local algebra of the singularity. Which encodes everything you could ever want to know about the singularity. So then what is the value semigroup or the value semiring? Well, it's just what we get by composing the map whose image is the local algebra with the t-adic valuation on this ring of power series. So either we look at power series that are non-zero, in which case the image of the power series, these non-trivial power series, is a subset of the natural numbers. So just remember that this t-adic valuation, by definition, is just computing the order of vanishing in t equals 0 of a power series. Or if we want to include 0, we have the same basic behavior, except that now the image is included in n together with infinity corresponding to 0. In the first case, so either way, if we compose the map of rings with the valuation, S is the image of the composition. Let's call this, yeah. And in this first case, you get the value semigroup. And then in the second case, I'm going to say that the result is the value semiring, which I just think of as a compactified version of this value semigroup. Very informally, I don't want to write this down, but I want to think of passing from the local algebra to either the value semigroup or the semiring as sort of a generalized version of tropicalization. In particular, the value semigroup and the semiring are closed under, so they're semirings with respect to the tropical operation. So S is so S is a semi, so when I say value semiring, so S is closed under tropical addition and multiplication. So in other words, addition is going to mean pairwise min, and multiplication is going to mean usual addition. So just to give sort of the simplest example of this in action, if we take the map that sends C bracket xy to C of t via x goes to t squared and y goes to t cubed. So this is the parameterization of a simple cusp, the usual simple cusp that you see in connection with an elliptic curve with a singularity at the origin. And S, in this instance, is just generated by the two exponents that appear here, 2 and 3. Okay? So this recipe explains what happens for cusps or unibranch singularities. More generally, if I have a singularity with multiple branches, there's a similar recipe. Oh, yeah. Okay. So in the more general situation, if I have a singularity with r branches, that singularity is parameterized by a ring map that now has as target a product of R power series rings. So and then S, the value semiring, is just the composition of the product of the t-adic valuations on the target with the ring map. So the philosophy that I want to promote here is that the topology of one of these decorated Savary varieties, where I specify that the images have a unique singularity of given type given by this combinatorial object S, is going to be controlled by arithmetic properties of S. So by arithmetic properties of the value semi-ring, and then the reason why I have matroid in the title of this talk is that ultimately the value semi-ring is going to be controlled by a matroid. And hopefully we get to explaining this last part a bit by the end. Sorry, yes, yeah, exactly. Thanks. Okay, so maybe just the 0th instance of trying to justify this philosophy would be explaining how to recover the genus of the singularity from the associated value semi-ring. So I want to briefly explain how that works. So again, when I say genus, what I mean is every singularity is going to compute a discrete quantity, is going to contribute a number to the to the total arithmetic genus of the underlying curve. So this is that number. So again, the simplest case to explain is the unibranch case. So in that case, a basic fact is that the complement inside of either the natural numbers or the natural numbers together with infinity of the value semigroup or semiring, let's take the semiring, is finite, and the contribution to the arithmetic genus is just the cardinality of that complement. So for example, in the case of the simple cusp, when S is generated by 2 and 3, so when I say generated, of course what I mean is I'm authorized to take arbitrary non-negative linear combinations of these two numbers inside n, or n bar, right? So there's only one number there's only one integer that cannot be realized in that way, and that's 1. So the genus in this case, the complement has cardinality 1, and the genus is equal to 1. Okay, so that gives the recipe in the unibranch case. How does it work for arbitrary number of branches? Well, the recipe is in terms of lattice paths. So in general, if I have S contained now inside of n bar to the r, what is the genus? Well, it turns out to be the following thing. It is going to be the number of, so try to give this a concrete instantiation afterwards, but so it's the number of unoccupied places in a lattice path. So this lattice path is inside of, so it's a lattice path inside of n bar to the r with unit steps that starts at the origin and ends in what's called the conductor of the semigroup. So what is this conductor? This, by definition, it's the minimal vector for which if I add n bar to the r to that vector, then I end up inside of the semiring. Okay, and actually there's an additional caveat here, which is I have to choose what's called a saturated lattice path, which just means that I maximize the number of elements of S that I pass through along my path. So for example, if I consider a simple node, in A2, well, so the simple node in the origin we can parameterize it by, for example, x goes to t1 comma 0, and so we just choose the axes, and y goes to 0 comma t2. And then it's not hard to see, actually, that the semi-ring that we end up with is just, so it's the following thing. It's the union of the origin together with the conductor plus n bar squared, where the conductor is 1, 1. So if we think about this pictorially, so the picture inside of n bar squared, say, is we have the origin, we have our conductor, and then the characteristic property of the conductor means that this entire quadrant belongs to S. So the unoccupied places, the saturated paths that are relevant here, are either I go origin to the right and then up, or I go up and then to the right. And either way, the number of unoccupied places is exactly 1. So G is equal to 1 in this case. Okay, so I want to say something about dimension counting. And upper semi-continuity. So the idea is the following. So if we require our maps to have singularities of given types, that imposes conditions on the coefficients of our maps. So, and we want to quantify combinatorially how that works. So these impose algebraic conditions on maps inside MND. And you want to count the number of algebraically independent conditions. Now, by analogy with the case of plane curves, in the case of the plane severity variety, what you might expect is that so a naive expectation might be that the codimension of M and dg inside of M and d be equal to n minus 2 times g. Actually, I have to explain this. Okay, so where is this number coming from? The point is that the point here is that the g-nodal sublocus inside of Mn dg has exactly this codimension. And why is that? Well, what you have to see is that conditions are additive across nodes, and that for each node, if I fix the preimage and the target, I impose 2n independent conditions. And then if I allow the pre-images, if I allow the target to vary and then the pre-images to vary, then each node contributes n minus 2 independent conditions. So, so the idea is that if M and dg were in the closure of the g-nodal sublocus, then this codimension would have to be the codimension of the g-nodal sublocus on the nose. And actually, well, there's just one, maybe, actually, what I said is almost correct, but there's one missing detail, which is that coming from upper semi-continuity, which is that Yeah, yeah. There's none of these, I mean, everything I say is going to require n is at least 3. I mean, when n is equal to 2, our method doesn't give anything interesting. But the other point is that, for example, if I apply upper semi-continuity of contact orders, what I see is that a hospital curve of genus G never specializes to a G-nodal curve. So the upshot is that it suffices so to conclude that MNDG is reducible for a given choice of N, D, and G, it's enough to exhibit a space associated with unisingular maps of type S for which the codimension inside of M and D is strictly less than this number n minus 2 times G. And I think...
Sorry, but
Yeah.
the remark was that for n equal 2, the codimension should be n minus 1 times G, right? It's just G. Shouldn't be n minus 1 G also in for arbitrary n?
No, because again, these are, the geometric genus is 0. The normalizations are P1. So all of these curves are, these are rational singular curves. So it should be 0. I mean, those are the generic, sort of characters in there. Actually, okay, so yeah, so I want to give 2 theorems. So one is about this situation when the cusp is of hyperelliptic type. Yeah, actually now I'm confused about. I'll come back to this afterwards. Let's assume that the degree is at least is at least the maximum of 2g minus 1 and n. Then we showed that the codimension inside of M and D of maps with hyperelliptic cusps is exactly n minus 1 times d times g. Whereas, on the other hand, if I consider degrees that are sufficiently large with respect to the genus, and n is at least 3, so maybe yeah, I'm confused about it. I mean, everything we do requires n is at least 3. What goes wrong when n is equal to 2 here? If I consider a generic semigroup, associated with vanishing orders given by a consecutive sequence of even numbers, starting with 2 times m, then what we can show is that the codimension inside of M and D is strictly less than n minus 2 times g. Yeah, I think, okay, so I think the point is just that I mean, when n is equal to 2, the generic maps are just genodal. So that's why this is a 0 here. Our methods are only interesting as soon as n is at least 3. Okay, so in the remaining time, what does this mean? Yes. So what I mean is, if you consider maps for which such that the cusp is given locally by after a normalization, t goes to t to the 2m plus higher order terms. T goes to 2m plus 2. then the idea is that these high-order coefficients these have generic coefficients. So a priori, it's not clear what the genus of such a singularity is. And you have to control for that. OK, so the last thing that I want to say is something about the situation for maps whose images have multi-branch singularity. And so the question would be, again, when are severity varieties of unisingular rational curves now with singularities of multiple branches reducible. And in fact, so just excess dimensional and therefore reducible. And let's focus on multiple points. So by which I mean these are just transverse unions of smooth branches. So something that looks like this. But actually, I want to impose, the important point here is that we can specify the number of incident branches, but also the embedding dimension, the local embedding dimension of the singularity. So for multiple points with R branches and embedding dimension L, the idea is that, so to count conditions imposed on rational curves by these singularities is easy. Because to impose that there are R branches through a fixed point, well, by a generalization of the count for nodes, each one of these incidence conditions imposes R minus 1 times n minus R conditions. But then, if we impose that the embedding dimension be equal to L, well, those are determinantal conditions because you can think of this as, so you can see that imposing that the embedding dimension be equal to L, that'll impose at most the number of conditions that you get by requiring a generic n by r matrix to have rank equal to L. So, so counting conditions isn't so bad. What's more delicate in general is computing the genus of such a singularity. And calculating the genus is delicate, except when there's exactly one situation when it's easy, except when the embedding dimension is equal to 2. So when L is equal to 2, or in other words, if the singularity is locally planar, the genus of the singularity is just going to be a binomial coefficient. And then if we now sum conditions, incidence together with embedding dimension, what we end up with is something that asymptotically is strictly less than n minus 2 times g whenever r, the number of branches, is large enough. So, so in particular, those severity varieties, the corresponding mndg are reducible. So the very last thing that I want to say is that so we showed that in general the value semiring, and this is useful if you want to think about what happens beyond locally planar multiple points. So the value semiring is additively generated by elements of minimal support. So when I say minimal support, what I mean is we want to maximize the number of entries that are equal to infinity. And the fact that that's true is actually a reflection of the fact that S is a homomorphic image of what I'll call the tropical support semiring, which is just a slight generalization of a matroid. So it would be a matroid, except it's on an infinite number of labels, so we call it a finitary matroid. So what is this tropical support semiring? Inside of the product of power series rings, in which the local algebra of the singularity lives, we just record exactly those monomials that appear as supports of elements of the local algebra. And there's naturally a semi-ring structure on that set for which addition is just union of supports, and the product is a Minkowski type sum. So if I have just a minute, I wanted to show one last slide, sort of trying to justify why this last result might be useful. If we consider a 4-tuple point in 3 space, I want to compute the value semi-ring of that singularity, and in particular what its genus is. And we can do that using this characterization of the generators as elements of minimal support. So how does that work? We have a parameterization of our singularity, which is given by this map of rings. Minimal support means that I want to maximize the number of zeros that appear I want to maximize the number of infinities that appear in elements of the value semi-ring. So that comes down to annihilating particular coefficients. So for example, if I filter elements in the local algebra according to the degrees in the ambient local variables, if I consider linear elements, for example, if I have linear combinations of x1, x2, and x3, well, the idea is that you substitute for x1, x2, and x3 these 4 tuples of linear forms, and you want to know how many entries you can set equal to 0. And that's, if you make genericity hypotheses, the number of elements you can set equal to 0 is just prescribed with a rank and nullity theorem. So you can calculate the elements of minimal support associated to linear combinations, and then you can do the same thing for quadratic elements, or elements that are linear combinations of quadratic monomials in the ambient variables. And again, and now the point is that once you have the quadratic elements of minimal support, every entry but 1 is equal to infinity, and that means that in particular, if you sum those 4 generators to infinity, 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 and its permutations, the conductor is forced to be, sorry, I guess it's rather that you'd be, yes, if you sum them together, then you get this conductor 2, 2, 2, 2. And so, yeah, so then it's not too hard to see that a saturated path from the origin to this conductor, an example of such a saturated path is the one that I've written down here, in which 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, and 2, 2, 2, 2, 1 are the elements in the complement of the semi-ring, and consequently the genus is 4. So thanks for your patience. I'll stop here.